Okay. Uh, yeah. I think I don't have a question about this, so I see some code. Chapter. All my source code I already uploaded to the Blackboard. Chapter. Right? Really? Memory layout. Okay. Okay. This is a source code. This is the code for that memory layout. So let's say this will print it out the address of the. This will print it out the address of this is what? So percent %P is the address, memory address. And what about this? Not good at C programming. We know that. What's this? What's this? Main is the function name. That's the main function name. What's this? Void. Yes. Void. No, it's a pointer to a function. Main is the function name. Okay, this is difficult part of C programming. You see, main is our function name here. Main is our function name, and then this is the address of the function main. Address of the function main is text segment. Function main is our source code, like the compiled source code. So it's in the text section segment text. Never text size. And white size is in the way we transfer to is pointer word type. So make it easy to print it out because this percent P don't have some type. We only print it out it's the pointer. And this one simple. This is X, Y is in the data section. If you forgot that, come back to here. Data. Initial data or uninitial data. Sometimes we call this BSS section. So different names. Data section. X and Y. And this is the local variables. This is the values. Values is what value is what's this? You see in the C programming, we always have this symbols. This symbol is the general address of values. What's the values? Values is pointing to a local member here. So this will print it out the memory address of pointers value. Okay, good. So that's an address of a local value pointer. So value is a local variable. Value is a local variable. It's a pointer, local variable. It's a pointer to a local memory address. This one. Any question to this? A little complicated, right? So what's the printing out? What are you printing out? Oh, this one is the array. Array is parameters. Array 0 is the parameters. This one. And then I also say this one. I also printed all the values of this array. Let's say this one. This is out of bound. Out of the array bound, and this is the value that's definitely out of the bound, right? It's illegal. I can set to the random number, any kind of numbers, and I can print it out. Let's see what happens. Here, I don't forget that free the memory. Okay. Okay. Drag to the file and compile and run. You see here, this is output. So the memory address is increasing, right? This is a text segment. This is the data segment. This is the text segment. And this is the heap segment. So it's increasing. Remember our memory data, the text segment is the lowest memory. And I guess the stack is the highest memory. Text is the stack, highest memory. And the stack is grow down, paper is grow up. But here the paper location is totally different from ours. There's a difference? Paper. This is the memory allocated on the P. This is totally different with ours. Why? Why it has like this? The first question. Okay, this is the I try to ask you, but it's difficult on let you answer now because current operating system has a protection mechanism. It's a safety private. It's a safety program to make this memory safe. Okay, so this heap is mapped to other memory. Right. This is the modern operating system. So that you cannot easily access it. For example, here this is our array. Okay, access printed out is good, but value 5 is illegal. It is illegal, and the value 100 is also illegal. Right, it's in the heap, and the compiler never give us the error. As I can compile and run it, and the compiler never give me an error, and I still can access this memory address. And still I can write the value to this memory address. It's a heap. So it's not safe. It's not safe. So attackers may use this feature to do what? To modify the value of a memory address, the heap. If this memory address is the username and password, what happened? So I can modify the username and the password. So in the modern operating system, the heap, the memory address is different. So that you're too hard to find what is where is the username and where is the password. So the modern operating system is hard to do that kind of attack. But old ones, maybe in your older machines, the heap, you can make a very careful calculation of find out, oh, where is the username, where is the password, where is this information located. I use this pointer to access this heap memory. So here, the C compilers never give us error. It still can run and modify the values. So yes, it still can run. The program is still correct, but you modify this memory, and they will give us bugs or blue screen. Maybe in future, you don't know that. So that's why I say C programming is hard. The memory management is really hard. Yes, here. Good. Any questions here? Very good. That's why I recommend use Rust. Rust does not allow you to do this. And I came across lots of bugs writing like this. Compiler never give us an error, and I run a test. The result is good, but in future maybe cause some unexpected errors or bugs. Okay, let's back to here. Process statement. Last class I will going to here. Slide show. Okay. So last class we're going to here. PCB, process control block. The process control block is to store information of each of the process, like state, process number, process counter, register, memory limit, list of all the open files. So all of the information of this process is stored in PCB. This is the kernel, Linux kernel data structure. You cannot see in the user mode. It's kernel mode. The kernel data structure. Let's use it to store all of the information of the what process. So it's called a process control block. Okay. So far, processor has a single thread executor. So one process has a single thread. And it's possible that one thread can have multiple threads, right? So yeah, PCB also includes status of all of the threads, right? So we will discuss the detail of the threads in the chapter 4. Okay, remember, now just remember that one process have one thread. It also can have a multiple threads. Okay, this is the current data structure of the PCB. You say, PID, process ID, state, and schedule information. Because we use this PCB for what? Most important feature is for scheduling. Okay, and list of the children. So process have the children and the parents. List of children and the parents, and structure files. List of all the opened files. Is all of the pointers. So it's allocated memory in the kernel to store this information. So here is the pointer. Okay, and this is the address space of this process. So and they link together and double linked list. All the PCB double linked list in the okay. So we have lots of process. The important feature is how can we schedule that? Because like my laptop, we have thousands of processes, but only have a 8-core CPU. CPU only have 8 core, so it's not enough. So that's why we need a scheduler to find out which one will execute in the CPU and which one should put into sleep. This way need a scheduler. So this way need a process scheduler. Select among available process for the next execution on the CPU cores. Okay, here why we need this scheduler, because we only have 6 cores or 8 cores. Good CPU has 30 cores, 64 cores, but no CPU has thousands of cores. Okay, maintain the scheduling queue of process. We need 2 queues, ready queue and wait queue. Okay, we will see the details later. So this is the ready queue. So ready queue maintain the PCB. All the PCB put into the double linked list. It's a ready queue. When the CPU is idle, okay, it pick 1 from ready queue. The ready queue has had until say pick 1 from ready queue to execute, right? And this is the wait queue. So all this process wait. The scheduler can only work on these 2 queues. So scheduler will pick this ready queue. So as lots of threads are ready. So which one I should pick? Which one CPU should pick? That need a scheduler. Which one should pick? And the wait queue, which I should put into the head, are not into the tail. This is the work on the scheduler. Okay, good. Anyway, it's good. And for scheduling, we need a context switch. Like this. P0, the process P0 is executed. And it's interrupted by the interrupt. Here's the interrupt. Interrupt or system call. System call is one kind of software interrupt. Right? The interrupt will. What is the interrupt? Do you remember? The answer? Interrupt. What is interrupt?
Let's say we don't have the right resources or something happens that has to.
Yes.
Like an emergency, then we'll shut down.
Like a system call, this P0 need to read or write files. So the P0 here must stop. Wait. That's called this is the interrupt. And so when the interrupt comes, it's firstly save state to PCB0. So process P0 on the PCB P0, save all state to the P0, and then this P0 become sleep, see, idle, sleep, and never execute. And the operating system will reload the state of PCP1. It's a process one, P1. Wake up. Okay, so the P1 is the sleep just now, just wake up. So this is idle. The P1 is sleep because the P0 is wrong. So when the CPU is idle, the wake up the P1 and exactly. It's a P1 is interrupted by some interrupt or system called P1 going to sleep at the same state to PC1. And then what? Reload state for PCB0. See, this is a one core CPU. It cannot run in parallel. Like it's just a one core CPU. It cannot run in parallel. But P0 and P1, it looks like they running at the same time, but not. CPU can only execute the one process at one time. And if the P0 is busy with reading or writing some files dealing with some interrupt, so the CPU is idle. CPU is nothing can do. So why we not? That's why the CPU doing the context switch from P0 to P1. That is, switch from P0 to P1. So all is controlled by what? PCB. PCB is a process control block. The processor must save all his state to the PCB. And the next time I can wake up. Okay?
So when it says PCB 0 and PCB 1,
yeah,
that's just one PCB, and then you're looking at slot 0 and slot 1, so to speak. They're not separate.
No, it's separated. So PCB 0 is for process P0.
So they're each on separate blocks.
Separate. So all the PCB is listed by double list.
So does every process have its own process control block?
Yes.
Okay.
Okay. Okay. No. Yes, it is. Every process has its control PCB, process control block, and they linked with a double linked list. Double linked list we can use a head. So we can, I believe you already have this class of data structure. We can use the head to traverse all of the process. Or we can use the tail to directly find the last one. Right? So if we want to access this one in the middle, it's impossible to directly get into the middle. We must travel from a head going here. Because it can save the memory, it can save some memory space, right? We only need head and tail and link them together. So each of them has a process control block. Okay. Yes, context switch, important concept. And the current, so no parallel processing, this one. And the current CPU support this context switch in the hardware level. So they have they design some specific instructions to support this. Okay, this is the context switch. Okay, I already explained this clearly. Here. So context switch is a pure overhead. Context switch don't do calculations, right? They are purely overhead. So the CPU is busy with a switch from a process 0 to process 1, but no program, no computing. So the system does not use for, it's not used for work for switching. The more complex OS the PCB, the longer the context switch. The PCB is very complicated, and there's a huge number of the PCB, so they take more time to context switch. So in some circumstance, it's possible that the CPU is busy with the context switch. Looks very busy, 100% busy, but make no progress. This has happened. This always happens. So this is the good and bad things. Good and bad. If no context switch, so the CPU will not fully used. The CPU is always idle, waiting for some process reading or writing file. CPU always idle because the CPU is very fast. Read or write file is very slow. It takes seconds, several seconds. But if the operating system always doing context switch, no computation is done. It's still meaningless work. Okay. Time depends on the hardware as well. Like I say, this context switch is very important. So the hardware already supporting the hardware. They have some instructions like save the PCB state and load the PCB state, the hardware. Some hardware provides multiple set of registers. They can use the resistor to speed up. Because it's always happen in the CPU. Because we have thousands of process, but have 6 cores. It always happens some process put into sleep, some process wake up. So if the hardware can support this, use some high-speed registers. Because a register is why is a register not memory? Why is a register not memory? Why the CPU don't support this from a memory or from register? Yeah.
Registers are a lot quicker.
Yes, it's the most CPU is the most efficient, and memory is very slow. Memory speed cannot catch the CPU speed, so that's we have some registers. Yeah, do you remember the first class? We have a hierarchy of the speed. Memory, CPU, register, then 3 levels of CPU cache, and then it's memory. The memory is much slower compared with the register. That's why if we want the CPU to efficient to switch, we must use register doing this. But register is very small. Only take 10, 16 variables. 10, 16, very small. It's very quick. Good. Okay. Operations on process. Now it's programming. So process creation and process termination. A system must provide this. How can we create a process? How can we terminate a process? The process we are focused on the Linux world. So the Windows is similar, but different with API. So Linux, every process given an integer. So in the Linux, always have the integer for ID, the PID. PID is the integer for the ID of a process. And a process must have the parent process. And they can create another process. This is a child process. And the parent process create a child process. It uses a system call. So do you still remember what is system call? Use a system call. Use a system call. What is system call? Try, yeah. No, I always ask the question. Okay.
I hold kernel, right?
Yeah. So because the create process is create process, you cannot create process in the user mode. So in the kernel mode, it will create a process. So the system call is to in the user mode. How can we in the user mode let the kernel know that I want to create a process? This is the system call. User mode and kernel mode are two different. I just many times. It's a memory layout is different. It cannot access each other's memory. So the user mode cannot see the kernel mode's memory, and cannot directly call this process creation. So they must use the system call and then create other process, form a tree, the tree of a process, and then it add a PID to the process. And let's say a tree. What is a tree? So this is a process tree. So PID is a system process. It's in the kernel. The kernel only has one process. Not shown here. The system process. Kernel has only one process. So the kernel memory is shared by all of the threads in this process. And this process can create other process like Python. I said all the computer use Python script to create Python, create a log ID. Oh, there's a mass logging. This is the shell, create a C process, and there's a logging process to create the bash. Create bash, can run the command lines. Command lines create two processes: PS, VIM, Right. So this is the process tree. This is also the SSH. Oh, this is SSH. Not shell. That's the shell. Create two SS, this SS. So if we have we have the process tree. Process tree. This tree is this is the parent. This is the children. And this is the parent and this is children, right? So every process must have the parent and may create several children processes. So parent and children. Good. So in this we can with the parent and children we can do some synchronizations. Okay, here we use the Unix example, Unix or Linux example. With in the Linux world, this is a fork and exists exactly is a system call to create the process. This is a Linux API, right? Windows are different API, but similar things. So the parent will create a parent we are doing the fork. This fork will split this process as two. Parent process is same as this one, and then it's a child process. So according to the return value, so if the PID is greater than 0, is the parent process. If the PID equal to 0, is child process. Then here, the parent process can call wait the child process to finish. Then parent process can quit. So wait can use for synchronizations. Otherwise, the parent don't know where's my child. I lost his child. This wait will wait until the child process terminate, and then the parent process terminate. Good. And okay, important is here address space. Address space. We say the process have a independent memory space. The child will duplicate. The child will duplicate the parent memory space. And then the duplication happens in the fork. The child process duplicate all of the memory of parent memory. And then they are totally different, separate. Yeah, separate. So then the memory, the parent cannot say the child memory space. Child also cannot say the parent memory space because they are totally different memory space. They cannot see each other. Okay, here I have a code. So it's the fork on child process PID. So after it's fork, in your mind, so you must imagine that this program split as the parent and the child. It's not sequential running. It's running for two processes together at the same time. So this is if it is less than 0, the error happens. And if the 0 is the child process. And if the parent, if it's greater than 0, it's parent process. And you use wait. Now it's this line and this line will execute at the same time. Can you imagine? The same time. Forgot about some sequential running. This is the parent and the child, and until here is the same time. And child will run this command line of ls, and the parent just wait until the child terminate. Until here is good. Let's say some okay, I prepare some examples. Okay, good. Okay, good. This what's the output? Let's try. Okay. I say what's the output? Say this is This one is printed out by the parent. This parent PID. Okay, I am the, oh, where is it? I am the parent as the PID. The parent PID. And then is I am the child. The child will run in ls command line and show all of the files in this folder. And then parent will wait. The child terminate, and the parent child complete. Then child complete. Parent will wait the child complete and print out child complete. Okay, so that's why you say the ls is not missing something. It's not it's impossible that the child process is running in the halfway that the parent quick firstly. So use wait. So the child process printed out all my files that is terminate. That the parent process printed out my child complete. Good. So in your mind, it's a two process running same time, not one. But in this window, the printed out is sequential printed out. The hard to imagine. Right? The sequential printed out. Actually, they are running at the same time. Because of the context switch. CPU, even it's running on the one CPU core, but we have the context switch. It's a switch on the different context switch. Seems like they are running at the same time. Because here, the output to the screen is very slow. And it's a system call to output very slow. So the CPU time will switch to other process, right? This is very slow to print it out, but CPU is really fast. Good. Any questions? I have another good examples. Okay. CSM code. Can you imagine what is the output? Because this is a child process, right? It's a fork. This is child process. In the child process, I modify the numbers because the number is a global variable. Initialize the global variable from 0 to 4, and I change the value in the child. But in the parent, nothing. So what's the output? Does it print out the same value? Yes or no? Same value. Same or not same? There's only one global variable. It's modified in the child, but not modified in the parent. Do they print it out the same or different? Oh. Yeah.
Maybe the same?
Are you sure it's the same?
No.
Okay, this is important. Yeah, it's important. I must say it's a very important concept. We'll learn this course of ordinary system. Same or not same? Yeah. Given one.
So Chinese point time.
What?
2.5
Yes. Different. The child memory and the parent memory are. The child will duplicate the parent memory. So after the fork, their memory are separate. They don't have relations, right? You modify the child memory, and the parent don't modify the memory. They are different. So like this is already adults, so they don't have relations in the memories. So let's say the output. Hey, what's the output? Hey, what is the output? Here. So you say the child is oh yeah, it's the operation. The child, the value in the child is modified, but in the parent is still not changing because their memory space is independent with each other. They never affect each other. So that's the fork happens. the fork will duplicate the memory. What happened?
Why is it negative?
Because of here, here, the source code is here. Yeah. Yeah, right? Okay. Sorry?
Like down the, yeah,
Down?
like one in decrements.
I cannot.
It's multiplied by the negative of itself, so.
Okay, I can.
0, 1 multiplied by negative 1.
Okay, this I suppose you know. So it's equivalent to this one.
I think it's just hard to see, you can see the asterisk, the plus, like that's probably why I thought that.
That's
I think he was just confusing it,
oh
plus instead of an asterisk.
Yeah.
yes, now it's good.
I got it.
Ready? Yeah. Yes, it's correct. Oh, I'm not sure. Is it correct? It should be okay. Great. Okay. Check the I never realized this. I forgot that. Check the Google it. Find out what this symbol means. I remember it's this one. And you know, these symbols in Python never allow this. This is really sometimes confusing. I already forgot this. Okay, save. Okay, let's back to our. Okay, this is used to show that the memory space is different. Okay, good to show in the code. Good to show in the code. Okay. Terminations. The process execute last state and then ask the operating system to delete it using exist system call. Exist system call will release all of the resource. The process will quit, terminate. It will release all of the resources, including allocate the memory, all of the memory, PCB, open the files, all of the resource. Yeah, will delocate from the operating system. And if this process has memory leaking, it's always deleted. That's why sometimes your some of the programs, the app, is running very slow. It's running very slow. That means memory leaking happens. Take too many memory. It's running very slow, and you close it and reopen again. It becomes good because the process, the quit, the exist will release all of the memory source. It is controlled by the operating system. Okay, but it's not a good idea that users always quit, terminate. Good. Let's go on. Process termination. Some of our operating systems do not allow children to exist if the parent has a terminate. If a process terminated, then all its children must also be terminated in some operating system. But in Linux, not. I tried in Linux. Linux allowed that parent quit firstly and the children quit later. This is called cascading terminations. All children, grandchildren are all terminated. The cascading termination. The termination is initialized by this is controlled by the operating system, or terminator. So this process creates lots of children, and they can terminate using cascading terminations. And the parent process may wait. That this is supported by the Linux. Different operating system maybe have a different strategy. This is some operating system. I don't know. I will check next time. This is for Linux. Linux can wait. Use a wait system call to wait a child terminate firstly, and then parent can terminate. If the no parent wait, if the parent is no wait, parent will not wait, and the parent will quit. Maybe earlier than the children. So the children will become a zombie. Or if no parent wait, the children process becomes zombie. And if parent terminate without invoking wait, it's a process become orphan. So that's the parent create firstly, and the child become a zombie or orphan, and it's there's no parent. So all this so the initial process, PID is the one in the kernel, the PID. So will there's a zombie or orphan. The initial process will become the parent. So we will not cover too much in this class. If you are interested, you see these links. The zombie or orphan. This is very useful when your operating system needs some process that is always run in the background. Nobody can terminate it. So they use this technique. A little complicated. They need to create a process and the parent create firstly, and then nobody can terminate it. It's always running in the background. Good. Okay, multi-process architecture. Multi-process architecture is currently widely used. All of the apps, applications, the programs, like there's a Chrome browser. So I suppose everybody use the Chrome browser. I use the Chrome browser, right? The browser maybe have one process. If we have one process that manages the user face, disk and the network, and one process to render the web page, like dealing with some HTML, and one process to dealing with the plugin process for each type of plugin. Right, three process, and many web browser. But some browser has only one process. The problem is if something happened, for example, if one process in trouble, it will crash. It's one process. But the Chrome is multiple process. If one process in trouble, the Chrome will not crash. The Chrome will create another process. So it provides a better user experience. Multiple process. It's good. But in your mind that the process cannot see the memory space of a process independent. They cannot see each other. But in this is the one application, right? The process must communicate with each other, right? So yeah, they must communicate with each other because they are same app. So what to do? So the Linux have the mechanism technique for IPC. So this is called inter-process communication, IPC, for different processes communicate with each other. We can use some shared memory, and we use some method passing. Okay, shared memory. I guess shared memory is here is important to show that concept. So you can see process A and process B. This is the memory space. This is kernel. This is the kernel mode. The memory space is the kernel has its own memory space. And the user mode have the memory space. And the user mode memory is split to different process. Process A and process B, maybe process C, thousands of processes. Each of the process cannot access the memory, access the other process memory directly. So process A cannot see the memory as process B. But they want to communicate what happened. They can create a shared memory. This shared memory can be accessed by two processes. Right? The process create a shared memory. Get here? Any questions here? Process create a shared memory. And then they can pass in some messages. So process A can put some values into this shared memory, and process B can read these values from the shared memories. So because process have a independent memory space. So this is a little complicated. I can show this source code. Little complicated in Linux. Okay. So this code, we can directly go to this. So this process. This process want to send this message to the other process. How we can do that? We need to treat the shared memory segment. We create a shared memory. Then we configure the size. Okay, configure the size. How much size of the memory? The size is 4096. 4096. And mapping the shared memory to the process. As I say, the process has its own memory space. Right? Without mapping, how can this process accessing other memory? So this is to mapping this shared memory to its process memory layout, memory space. Get it? I hope I explained clear here. Create a memory. We create a shared memory, and it must map into this process. So in this case, the process can access this memory. I think it's a little difficult to do because we not yet discussed the virtual memory. Virtual memory is later. I think after we discuss the virtual memory, you will come back, you will understand. Then it's write to the shared memory regions. Write to shared memory regions. Okay, let's run it. Shared memory. Hey, what happened? Nothing printed out. Because because it's right. PTR is what? PTR is the pointer to this shared memory here, and it's pointing the value to this shared memory. Printf, as printf is print not to a screen. It's a print to a memory space. And PTR is our shared memory here. Okay, PTR is this here. PTR is shared memory. So this value is already printed out to the shared memory. Okay, and this process already terminate, but the message still keep into that shared memory because this memory not released, and this shared memory is not part of the processor. If this is part of the process, this process terminates and all the resources terminate. Okay, get it? And then I run this the other thread because they recognize by each other by the name OS. OS is the shared memory name. And use this name to find out the. Okay. Say hey here, the message printed out. So the other threads, sorry, the other process create this shared memory and use the same name, and they can use the same name, same size, same size, and still mapping to this process memory space, and then read and print it out, print it to the screen, printf, and you can see the message. This is a message passing between different processes. Okay. It's possible, but it need you to mapping this memory space into the process. Clear here? Good?
Is it the name is what connects the two?
Yeah, it's the name. It's the name. The name is better than idea. And then we can make some very fancy names. This name. See, the name is used. This name is used by where's the name? Yes, open it here. You open it as a shared memory FD. This is the ID of the memory space. Then mapping this ID to this process memory. Good. I think this is a template. Will you use
at the bottom of this code, you have that line that says print F.
Mm.
To the screen.
Yes,
If you were to have that in the other code, would it not work?
it works. It works. In this code, if you print F, you can still print out the message. But as printf is print out to the memory, not print out to screen. You can still print out to the screen. Let's try. Let's try. Okay. Print F. It's a PTR. Okay, we have source code. It's good. We can try. Wait, what's PTRs mean? Okay, what's the print down? Oh, it's because this PTR is a pointer. It's a pointer. Is not a char. I must transfer into the char type. Oh, it's not printed out. Why it's not? Because this PTR is you see it's increased. The PTR is not pointed to the string. Now it's pointed to the PTR is from the head of string. Now it's pointed to the tail of the string. It's always increased. It's always increased. So that's why it's pointed to nothing. Okay, you can try later. I will upload this source code. Play with it. Good. Okay, we can save our time to other topics. Okay. Okay. This is a one. Okay, take a break. Take a break. 10 minutes. Let's come back. Any questions? Ask questions.
I think it's this class. This is. Yeah, this is class.
Yeah, in the, sometimes it's a go with random, what is it?
Yeah, random questions. I never not let me know when to click. Maybe next round, maybe election. You probably.
Is it? Said we have today.
No, this is what we all be working. Yeah, speaking that time, I can come in. The quiz is always like what is right? What is the process? You can write quickly, you can write. But next time you not right. But I mean, for the time this for sometime while later.
And for the quiz, you basically want to, there's attendance, does it have to be correct, or is it only like 10 minutes, right?
It must be, no, it must be correct. Our master will master. I think it's also, this the customs, it's all from the like. Not even check the knowledge, check the knowledge. No. Not no, oh, I should not tell you. The random pattern. Random pattern, it's only I can tell you before the class, no, right? Yeah. Alright. That's the old.
Only that I'm Mariam. You know how you have Zoom for one person, Mariam?
Sorry, I can't,
I told you that I won't be watching the lectures online on Zoom.
oh, so it's you that's, let me
Yes.
to, oh. Mariam,
I'm
you
the
said
one
me,
who's doing it as a reading course.
reading course in the winter. Oh, yes, you said this, let's talk about here. So then, you want to do this reading group in winter?
Yes.
Can you do this, this time?
I will need to pay attention.
Okay, attend the lecture, good,
Yes.
attend the lecture, finish all the assignments. Yes, and in the reading class, like we have a meeting. Show your assignment, I will answer the question, if you answer my question, I give you the marks. Yes. But before the meeting, you must pick out all of the details. Yeah, yourself, if you cannot answer my questions. You'll get very low marks. Yeah, thank you.
So there will be five, or later on, we'll just do that.
Final exam, yeah, we can do a final, it's easy, we have a meeting room, we do a meeting room, do the final exam. Yeah.
And if I do it, I should like come to your office.
Yes. Yes, final exam, maybe I ask you questions, like, all the questions of final exam. It's the same thing, answer my questions, I will get a good mark. No, usually you answer my question, you cannot use the chat meeting.
Okay, in
Because
person.
in person, I ask you, you answer.
Okay.
If you cannot answer, you cannot search online, so you, yeah, that's a,
That's fair.
yeah, yes.